Fourier transform, part 1. A common engineering technique is about partitioning all the complex problems into simpler ones. So when the simpler problems are solved, the total solution would become the sum of the simpler solution. So basically, there are 3 requirements that you should fulfill. So the first one, the problem should be expressed as a number of simpler problems. Second, the problem should be linear, meaning that the solution for the sum of function must be equal to the sum of the solutions. And number 3, adequate accuracy, where the contribution of the simpler solution to the total solution must become negligible after considering a few terms. Why is it the need to represent your signal in frequency domain? Because in many cases, it is much easier to analyze the signal in terms of frequency. Let us look into the 3 figures on top. So you have figure 1, figure 2, and figure 3. So these signals are in time domain. By looking at these 3 signals, there is not much information that we can get. However, if we change these 3 signals into frequency domain, like the 3 figures at the bottom here, it will make more sense to us. So why bother with the Fourier transform? So Fourier transform is when you use it to change the signal from time domain to frequency domain or vice versa. So certain important operations on signals are more readily analyzed by using the Fourier transform. Example, when you use the sampling form, the modulation, the filtering, and so on. So let us see the Fourier transform table. Okay, over here, you have the xt. So this is the signal in time domain. And then this one over here, at omega. So this would be the signal in frequency domain after you have performed Fourier transform. So when you have, say for example, number 1, when you have the signal exponent minus at times with ut, if you apply Fourier transform, you can straight away use this equation 1 over a plus j omega. So that would be the signal in frequency domain. Let us look into the first property. So the first property is the linearity. So when you apply Fourier transform of x1t, you will have in frequency domain, it will become x1 omega. What if you have another signal x2t? So when we perform Fourier transform ft, we will get x2 omega. So the linearity property says that when you have a1 x1t plus a2 x2t, so we want to perform the Fourier transform here, it will become a1 x1 omega plus a2 x2 omega. Right, number 2, when you want to change from xt into x omega. So what happened for the conjugate? So if you have xt conjugate, okay, in frequency domain, it will become x conjugate, but in negative form, it will become minus omega. So for conjugate symmetry, when you have x minus omega, it will become x conjugate omega. The time frequency duality of Fourier transform. So here you have forward ft and inverse ft. So if you have time domain as t, it will become the integration of xt exponent minus j omega t dt. And if you want to change it into frequency domain as omega, it will become 1 over 2 pi, the integration of x omega times with exponent j omega t d omega. Next, we have the duality property. So consider the Fourier transform of a rectangular function. So here, this figure is showing you the signal in time domain, a rectangular function. So if you have rectangular t over tau and you want to transform it into the frequency domain, so we use Fourier transform, it will become tau sinc omega tau over 2, which is represented by this graph over here. So this one, you just have to follow the table. Next is when we have the scaling property. So when you have at at, so this is in time domain, so the scaling happens here at, which is denoted by a. So in frequency domain, it will become 1 over the magnitude of a times with at omega over a. For time shifting property, so when you have the signal at t minus t naught, so you have here minus t naught, meaning that there is time shifting over here. So the frequency domain would become x omega exponent minus j omega t naught. For the frequency shifting property, when you have xt exponent j omega naught t, and you apply Fourier transform, in frequency domain, it will become x omega minus omega naught. For the convolution property, so the first one we have time convolution. So you have x1t convolute with x2t. So when you apply Fourier transform, in frequency domain, you will have x1 omega times with x2 omega, meaning that if in time domain you have time convolution, in frequency domain, it is just the multiplication of those two frequency signals. So frequency convolution, when you have x1t times x2t, that will become 1 over 2 pi x1 omega times with x2 omega, meaning that if you have frequency convolution between these two frequency signals, it will become the multiplication of those two signals. So finally, this will be the Fourier transform properties. So here you have all the operations that we have stated earlier. So you have linearity, time shift, time scaling, time transformation, duality, frequency shift, convolution, differentiation, and integration.